Hi everyone. Today we're going to do chapter 3, algorithm analysis. I think it's going to be too much of work, so I'm not sure we can finish today. Maybe we can do part now and then during the week we'll do second one. There's too much explanation, but we'll see how it goes. Algorithm, it's a backbone of computer science, of coding. What is algorithm? Algorithm is a step procedure which is the finite set of instruction that, if followed, should be accomplishes the particular task. So must have a finite end of the certain task that you wanted to accomplish. Like e.g., let's say I wanted to go to town today. So the set of steps that I need to do, I must path, prepare the tax fare, take a tax, and then go to town, reach town. That's a set of finite of steps that I need to do to go to town. Yeah, that is algorithm. In computer, it needs to have a clear intention, clear plan. So it must have input, output, definitive clear plan, and then finite must have an end of steps and must be effective. In contrast with the main topic of the book, data structure. Data structures is a systematic of organizing and accessing the data. So we're gonna go with this. On our first section is in a classic story. The famous mathematician Archimedes was asked to determine if a golden crown commissioned by the king was indeed pure gold or not part silver, as informant has claimed. Archimedes discovered a way to perform this analysis while stepping into a bath. He noted that water spilled out of the bath in proportion to the amount of him that went in. Realizing the implication of this fact, he immediately got out of the bath and ran naked throughout the city, shouting, "Eureka, Eureka," meaning I found it, for he had discovered an analysis tool, which is displacement, which when combined with a simple scale and could determine if the king's new crown was good or not, or is it fake or real. That is, Archimedes could dip the crown an equally weight amount of the gold into the bowl of water to see if the both displays the same amount. This discovery was unfortunately for the goldsmith or the informant. However, for when Archimedes did his analysis, the crown displays more water than an equally weight lump of pure gold, indicating that the crown was not in fact a pure gold. In this book, we are intended in the design of good data structure and algorithm. Simply put, a data structure is a system of way of organizing and accessing data, and an algorithm is a step-by-step procedure of performing tasks in a finite amount of time. These concepts are central to computing, but to be able to classify some data structure and an algorithm as good, we must have precise ways of analyzing them. The primary analysis tool we use in this book involve characterizing the running times of algorithm and data structure operation, with space usage also being of interest. Running time is a natural measure of goodness, since time is a precious resource. Computer solutions should run as fast as possible, and generally, the running time of an algorithm or data structure operation increases with input size, although it may also vary for different inputs of the same size. Also, the running time is affected by the hardware environment, e.g. the processor, the clock rate, memory, disk, and software environment, e.g. the operating system, programming, language, operating system programming language in which the algorithm is implemented and executed. All other factors being equal, the running time of the same algorithm on the same input data will be small. Computer has, say, a much faster processor, or if the implementation is done in a program compiling to native machine code instead of interpreted implementation. So we begin discussing the tool for performing experimental studies. Yet also limitation of the use of experiments as a primary means for evaluating algorithm efficiency. Experimental studies, if an algorithm has been implemented, we can study its running time by executing its various test inputs and recording the time spent during an execution. A simple approach for doing this in Python is by running the time function of the time module. This function reports the number of seconds or fraction thereof that have elapsed since the benchmark known as the approach. The choice of the approach is not significant to our goal, as we determine the elapsed time by recording the time just before the algorithm and the time just after the algorithm, to be computing their differences. The time just before and the time just after. We call it a priori analysis. This is a theoretical analysis of an algorithm. Efficiency of the algorithm is measured by assuming that all factors, for example, the processor speed are constant and have no effect on the implementation. That is the time before you implement your algorithm analysis. And then we have the after one, which is posteriori analysis. This is an empirical analysis of an algorithm. The selected algorithm is implemented using the programming language. This is then execution on target computer machine. In this analysis, actual statistics like running time and space required are collected. This is after you run your, just after you've done your coding, and then you check how long does it take. So let's try and tap this one code. On time. On time input time. That's sign. That's a time module. This code, we import the module from the time module, and then we define the variable that start time, and then we run with this method time. And then here, that's where we're gonna run our algorithm that we're gonna type. Then this is the end of time. This is prior and then after. Then from here, and then we we calculate the time ran, which is the end of time minus the start of time. And elapsed time measured in this function is a distant reflection of the algorithm efficiency, but it is by no means perfect. The time function measures the relative to what is known as the whole clock, because many processes share use of computers as central processing unit or CPU. The elapsed time will depend on what other processes are running on the computer when the test is performed. A fair metric is the number of CPU cycles that are used by the algorithm. This can be determined using the clock function of the time modular, but even this measure might not be consistent if repeating the identical algorithm. On the identical input, and granularity will depend upon the computer system. Python includes a more advanced modular named time8 to help automate such evaluation with repetition of the account for such variance among the trials. This is the plot of how input running time affects our machine or determine the way. So the more at 0, you can see it here. The more input, which is 500, the more time also line is 6. So you see the line is going up linearly, or exponential is going up forever. The result of experimental study of the running time of the algorithm, a dot with a coordinate of n, which is input, and then t for time, indicates an input of the size and running time of the algorithm as measured at 80 milliseconds. We have challenges of experimental analysis, which are experimental running time of the two algorithms are difficult to directly compare unless the experiment are performed in the same hardware and software environment. Experiment can be done only on a limited set of test input, hence they leave out the running time of input not included in the experiment, and these inputs may be imported. Third, the algorithm must be fully implemented in order to execute it, to study its running time experimentally. The last requirement is the most serious drawback to the use of experimental studies. At early stages of the design, when you consider a choice of data structure or algorithm, it would be foolish to spend a significant amount of time implementing an approach that could easily be deemed inferior by a high level of analysis. Our goal is to develop an approach to analyze the efficiency of algorithm. So our goal is to understand the efficiency or effectiveness of the algorithm. First, allow us to evaluate the relative efficiency of any two algorithms in a way that is independent of the hardware and software environment. Algorithm performed by studying a high level of description of the algorithm without the need of implementation that takes into account all the possible inputs. Counting the primitive operation, the primitive operation such as designing an identifier to an object, determine the objects associated with an identifier, performing an arithmetic operation, for example, adding two numbers, comparing the two numbers, accessing and seeing the element of a Python list by index, calling a function, excluding operating executed within the function, and then returning from a function. Measuring operation as a function of inputs. Inputs are to capture the order of the growth of algorithm running time. We will associate with each algorithm function f of n that characterizes the number of primitive operation that are performed as a function of such input. So a function n you can just say is kind of a box. This is what's everything happening here. So we call it f of n. That's where the machine grant everything. So that's function. That's the one that is being counted. We perform the function in the input size n. It is a common function that arises in sequence. We will introduce the mathematical framework for comparing function to each other. Focusing on the worst case, algorithm analysis has what you call worst case, average case, and best case scenario, where we can say worst case, the maximum time required for a program to execute. The best case, the minimum time required for a program to execute, and then average is an average time required for a program to execute. Here, for most of the time, because it's good to check, to find the strongest algorithm, is to check which one is worse. So they're going to focus on the worst case scenario of the algorithm. An algorithm may run faster on some inputs than it does on others of the same size. Thus, we may wish to express the running time of an algorithm as a function of the input size obtained by taking the average over all possible inputs of the same size. Unfortunately, such as an average case analysis is typically quite challenging. It requires to define a probability distribution on the set of inputs, which is often a difficult task. Figure 3.2 schematically show how, depending on the input distribution, the running time of an algorithm can be anywhere between the worst case time, the best case time. For example, what if inputs are really only of the types A or D? An average case analysis usually requires that we calculate expected running time based on the given input distribution, which usually involves sophisticated probability theory. Therefore, for the remainder of this book, unless we specify otherwise, we will characterize running times in terms of the worst case as a function of the input size n of the algorithm. Making the standard of success for an algorithm to perform well in the worst case is necessary require that it all do well in every input that is designed for the worst case lead to a stronger algorithmic muscle, much like Trickster, who always practice by running in an incline, in a high hill. You can see the difference between the best case, worst case, which is I think A, input A and D are on a worst case, and input E on a best case. We have 7 function or mathematical way to discuss in this book, which are used in algorithm or to analyze analysis of the algorithm. We have the first one, which is called the constant. It's a simple function we can think of is the constant function. This is a function of f of n is equal to c. C is a constant number. C can be a fixed number, such as 5, 27, 2 to the power of 10. That is for any argument n, the constant function f of n assigned the value c. In other words, it does not matter what the value of n is. F of n is always be equal to the constant value c. Because we are most interested in integer function, the most fundamentally constant function is g of n is equal to 1. This is typically constant function we use in this book. Note that any other constant function f of n is equal to c can be written as a constant c times g of n. That is f of n is equal to cg times cg of n in this case. So f of n is the same as cg of n. As simple as it is, the constant function is useful in algorithm analysis because it characterizes the number of steps needed to do a basic operation on a computer, like adding two numbers, assigning a value to some variable, or comparing two numbers. So creating a value, say maybe num, num, why is it not? Saying num is equal to 2, that is you're using a constant function because you're assigning a value to assigning num to 2. Saying num n, okay, we can just say n is equal to, it means you're running the algorithm which is constant because you're just assigning, you're directly assigning the n to 2, which is equal to 2. And then we have what we call a logarithm function. Logarithm function is one of the interesting and sometimes even surprising aspects of analysis of the data structure and algorithm. It is ambiguous present of the logarithm function. The f of n is equal to log of n base b. For some constant b is greater than 1, this function is defined as follows: x is equal to log of n base b if and only if b to the power of x is equal to n. By definition, log of 1 base b is equal to 0. The value b is known as the base. This b is known as base. This one known as base. And then the most common base of the algorithm function in computer science is 2. Remember, computer science, we use binary numbers or binary system where it's either 1 or 2. So when you use the base and the log, it's going to be 2. So we just say log of n is equal to log of n base 2. So b is 2. You know that most handheld calculators have varying Mach log, but this is typically for calculating the logarithm base 10, not base 2. Human beings, we calculate based on base 10. Maybe because our ancestors use the fingers, which we sometimes call them digits. So 1, 2, 3, 4, we got 10 fingers. So then when they calculated, they base their logarithm base 10. Computing the logarithm function exactly for any integer n involves the use of calculus. Big weight here, but don't be alarmed. We can use an approximation that is good enough for our purposes without calculus. In particular, we can easily compute the smallest integer greater than or equal to log of n base b is called ceiling. For positive integer, the value is equal to the number of times we can divide n by b. Therefore, we can get a less than or equal to 1. For example, evaluation of log 27 of base 3 is equal to 3. Calculating log 27 is a log base 3, 20, we're looking for what is going to give us 3. Since, because we're using the mathematical rules, we put, okay, this base, 3 remain base. We take this x as exponent, and then we say equal to 27. In order to, which number that can give us 27 when it can have a base of 3? So 3 to the power of 3, that gives us 27. So we say 3 cube. So base is equal, they cancel each other, and then x is equal to 3. So the log of 27 base 3 is equal to 3. Which is equal to 3. So that's why they say log of 27 base 3 is equal to 3, and then you can either also calculate with 3 divided by 27 divided by 3, then we'll divide 3, and then divide by 3, which gives us 1. The log of 64 base 4 is equal to 3, the log, and then divide by 0 gets 1, etc. The logarithm rules where we say log of A times C base B is equal to, you can also do as log of A base B plus, if there's times here, if there's times here, if there's times here, and then it means you separate the base B, log base B of A plus, you give it plus, then log base B of C. If there's a division, you separate with a minus, and then if A is that was fast. If A is the power of C, you take C to be at the back here, and then log B of A. And then if A log of A, you just divide log of D to the log of D to the power divided by log of D, log of A to the base D. By conversion, the unparallelized notation of log n to the power of C, notice that the value of NP, we know the notation shorthands log power of C to the log of n to denote the quantity log of n all into C, in which the result of the logarithm is raised to power. And then we have the third one, which is linear function. Linear function, it's an important function that is linear, which is f of n is equal to n. This is given as this is given an input value n. The value, the linear function f assigned the value of n in itself. It means this function goes as a straight line. It's become linear. It's a straight line. This function arises in an algorithm analysis anytime we have to do a single basic operation for each of an n element. So when we're doing a list analysis or a list processing a list, like list of in Python, like let's say a number of apple or a number of numbers, 1, 2, 3, 4, 5. When we're running that process, we're running a linear function, which is f of n is equal to n. For example, we're comparing a number of x to each element of sequence of size n will require an n comparison. The linear function also represents the best running time you can hope to achieve for any algorithm that processes each of n objects that are not already in the computer memory, because reading in an n objects already require an operation. And then we have a fourth one, which is n log of n function. The log of n function is f of n is equal to n log of n. That is the function that assigned to an input n, the value of n times the logarithm base 2 of n. This function grows a little more rapidly than the linear function and a lot less rapidly when the quadratic function. So it's between the linear and quadratic function. Therefore, we will greatly prefer an algorithm with a running time that is proportional to n times log of n base 2 than one with a quadratic running time. We will see several important algorithms that exhibit running time proportional to the n times log of n base 2 function. And then we have the fifth one is called the quadratic function. Another function that appears after obtaining algorithm analysis is quadratic function. The engine f of n is equal to n squared. This is mostly used where we have nested loops. When you have a for loops after for loops within the for loops, we mostly use the n squared, the quadratic function. So the code run on the first loop, it run once and then go inside, and then go back to the outer loop, run once, as go inside, run inside loop. So this why you have the end loop. So you run the first list one on a linear function, and then go inside another linear function. That means that's where you means with n times n, which is squared n. The function f or f of n assign the product of n with itself, which is n squared. The main reason for quadratic function appears in analysis of algorithms that there are many algorithms that have nested loops, where the inner loops perform a linear function, a linear number of operations, and then outer loop perform a linear number of times. That's in the cases algorithm perform n times n is equal to n squared. The nested loop and the quadratic function can also arise in a context of a loop where the function iterates of a loop using one operation. The second case is using two operations. So you mean in a visual machine to get that output? I think yeah, you can have a logarithm that can be printed out in a visual machine. I'm not sure if I'm getting you.
Yeah, in the sorry about that. In the VS Code or the Python platform, can the logs be printed out? Yes.
Yeah.
Am I making sense?
Yeah. You can do a calculation of logs. Of logs. I think in the exercise, they have a question where we need to run a log.
Okay, thanks.
You also can import the modular math and then math.log, and then you run a certain calculation. The quadratic, because we have, I think, 4 minutes. Maybe for me, and then maybe we can come back and join. Great. The quadratic function can also arise in a context of nested loop, where the first iteration of a loop uses one operation, the second uses two operation, the third uses the three operation, and so on. This is the number of operation 1, 2, 3, blah blah blah, n minus 2 plus n minus 1 plus n. In other words, this is the total number of operations that will be performed by the nested loop if the number of operations performed inside the loop increased by 1, which each iteration of the outer loop. This quantity also has an interesting history. In 1787, a German school teacher decided to keep his 9 and 10-year-old people occupied by adding up the integer from 1 to 200. But almost immediately, one of the children took the answer. Teacher was suspicious for this. Then the student had own answer on his face, but the answer was 5,050. It was the correct, and the student was Carl Gosch, which is one of the best mathematicians ever have in time. The student, 2 minutes, but maybe I should have tried to do what the student did. You can see 1, 2, 3 until n. So the student said 1 plus 2 plus 3 plus ... and 98 plus 99 plus 100. And then the student can and then also run hundreds plus 99 plus 98, blah blah blah. And then from 3 to 1, 3 plus 2 plus 1. So the student realized when you add this 1 plus 100 become 101, and also 2 plus 99 give us 101, 3 plus 98 give us 101, 98 plus 93 give us 101, 99 plus 2 give us 101, 100 plus, so it says if there's a trend in this one, so you can just say 100 times 101, which gives us 10,100. So this number 2, they give us 10,000. So if we divide by 2, it will give us the total number of all the summation of this number, which is 5,000, the half of 1,000 of 10,100, 5,100. So that's how the great mathematician came into this answer. I think we left this few seconds, but also you can use a shortcut, what you call a summation, where you say 1 plus 1 plus 2, blah, 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 and then until n times n plus 1 over 2. So we know that n is 100, so we say 100 plus 1, that's 101, and then you say 2 times 100 times